Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on completing the square. So completing the square is just another method we can use to factorize quadratic trinomials. And the idea here is we make it look like a perfect square plus or minus something. I'll get to what I mean by that in a second. Firstly, let's have a review of expanding. So if I have something like this, x plus a number, a is just a number, and I square it, this is a perfect square. It's something squared. So I can use FOIL to expand this, or the quick way to expand a perfect square, square the first term, square the second term. That's positive because it's positive a squared. And what goes in the middle is 2 times the product of the two things inside the bracket. So this and this are equal. So notice when you take x, you add a number and then square it. This number, double it, and you get the coefficient of x. And then the constant term is that number squared. So if we have something that looks like this or close to that, then we can make it look something like this. So let's have a look at an example. So let's say we have x squared plus 6x plus, say, 14. So what I'm aiming to do is write it as x plus something squared, and then I either want to add something or minus a number. So what I need to do is first make this into a perfect square. So notice that if I want to put x plus a number squared, as I said before, if I double that number, then I get the coefficient of x. So the coefficient of x is double the number that goes in the brackets. So in this case, the number I need to put there is 3. But note, if I put a 3 there, for this to be a perfect square, I would need, because 3 squared is 9, I would need a positive 9 here. But I've got a positive 14. So what I can do is I can rewrite this. I can change this positive 14 into a positive 9 plus 5. So the reason that I wanted to write 9 again is because this number in the bracket, 3 squared, gives me 9. Now this part is a perfect square. This is equal to this, x plus 3 all squared. So I'm adding a 5 to the end, and I haven't changed the expression. So x squared plus 6x plus 14 can be written like this. Let's look at another example, and we'll do this one a little quicker. So let's say I had x squared plus 8x minus 20. I want to write this as a perfect square. So what I do is I take the coefficient of x and halve it. So I have that x squared plus 8x minus 20, it's going to be x plus 4 all squared plus or minus something. But if I square 4 times it by itself, that actually equals positive 16, right? So I basically need to add 16 here, but then also take 16 away because that will cancel it out. That means I haven't actually changed the expression. The reason I chose 16 of all numbers is because 4 squared is equal to 16. So I can rewrite this as x squared plus 8x plus 16. This part here is the perfect square, and then I'm left with minus 20 minus 16. So I'm left with x plus 4 all squared minus 36. Now this here can be factorized further because it's the difference of 2 squares. So when you have the difference of 2 squares, to factorize it, you take the first thing that's being squared minus the second thing that's being squared, and then the first thing being squared plus the second thing that's being squared. So 4 minus 6, they are like terms. Of course, 4 minus 6 is just minus 2. and then I've got x plus 10. So I have factorized x squared plus 8x minus 20 using completing the square. So what is important to note here is that you can't factorize any quadratic trinomial using completing the square. This one here, I wrote it as a perfect square plus something, but that's not factorized because it's not something times something, it's something plus something. It's not factorized. I cannot factorize this expression here because there's no rule for factorizing x squared plus a number, something squared plus a number. There's no rule for factorizing the sum of two squares. There is a rule for factorizing the difference of two squares. This minus here makes all the difference. So sometimes you'll be able to factorize, sometimes you won't be able to factorize. All right, let's look at one more example. All right, so let's look at the example where I have x squared minus 12x minus 13. I'm going to factorize using difference of two squares. So what I do is I take the coefficient of x and I halve it or divide by 2 to get minus 6. So that number is what's going to go in the bracket. Somewhere I'm going to have an x minus 6 all squared. So then what I need to do with that minus 6, I need to square it because that is the number I need to add on to the end. So minus 6 squared gives me 36, positive 36. So I can rewrite this as x squared minus 12x plus 36. Now, if I add 36, I can't just do that and not change the expression. I will also have to subtract 36. And I still have my minus 13 from before. So this thing here hasn't changed the expression at all. So the reason I'm writing this is because this part will be a perfect square. This part here is equal to x minus 6 all squared. It's minus 6 again because that's half the coefficient of what's in front of x. So now I'm left with this other part, minus 36 minus 13, which gives me minus 49. So now I have something squared minus something squared. I have the difference of two squares. So I take the first thing and subtract the second thing being squared, first thing being squared plus the second thing being squared. Okay, and then I can just collect like terms. So minus 6 minus 7 is negative 13. Minus 6 plus 7 is positive 1. So I've just shown using difference of two squares that x squared minus 12x minus 13 can be factorized as this. So I've used the difference of two squares to factorize a trinomial. Now note, if this here was a plus, I couldn't do all these steps. I couldn't factorize it any further because there is no rule to factorize the sum of two squares. So hopefully you haven't found this video too confusing. Please ask me any questions if you have them. This has been the luckiest maths teacher in the world. Have a great day.